So we have several different types of electrons and bonds that we need to describe before we start drawing Lewis structures. We have electrons that are shared by atoms that we can call bonding pairs. We have electrons that are not shared that belong to one particular atom that we call lone pairs. And then we have different types of bonds. So for bonding pairs, for example, here we have hydrogen and oxygen atoms, right? These are just the basic Lewis symbols with the number of valence electrons around them. Oxygen has 6 valence electrons, hydrogen has 1. Whenever they come together to form water, H2O, you have 2 hydrogens and 1 oxygen, and they bind together like this. They form chemical bonds together like this. So you will have the hydrogen sharing an electron, each hydrogen sharing 1 electron to form a total of 2 bonds. So 1 bond right there, 1 bond right there. So how do we label these? Each of these pairs right here that I actually pointed at are bonding pairs. So these are both bonding pairs right here and right here. And then whatever is left are actually called lone pairs. So this pair right here and this pair right here are lone pairs, and they belong specifically to oxygen. They don't belong to hydrogen. Now we can have several different types of bonds. The first one is just the single covalent bond. This single covalent bond is sharing 2 electrons, so it is composed of 2 electrons. So for example, this bonding pair that we have right here, 2 electrons right there, that's a single covalent bond. We can also describe the types of number of electrons around certain atoms. So I specifically want to point out the duet that hydrogen forms around itself. Hydrogen is actually one of those exceptions that we discussed previously that have less than 8 electrons around it. So most atoms like to have 8 electrons around it. Hydrogen is one of those exceptions that is perfectly happy with just 2 electrons around it. So hydrogen can only form 1 bond, and it will have a duet around itself. But most elements will have that octet that you can see here for oxygen. So we actually have more than one type of covalent bond, more than just that single bond. We can actually observe double and triple covalent bonds. So for double covalent bonds, you will have 2 atoms that share 2 pairs of electrons. So for example, here whenever 2 oxygen atoms form an oxygen molecule, diatomic molecule, so O2, this is how it actually forms. You will share 2 pairs of electrons, or those oxygen atoms will share 2 pairs of electrons. So you'll have 2 covalent bonds, and we call that a double bond. So it's a total of 4 electrons, 2 bonds, we call it a double bond. Here you can see that they are both forming an octet, so that's the reason they form those 2 bonds, because that ends up making them happy. Remember, I like to think of it, okay, how will elements be happy with the 8 electrons around it? We also have triple covalent bonds, and this is when 2 atoms share 3 pairs. So here you will have 6 electrons being shared total. So you can see them here, and how we depict them as like lines, as bonds, is what you can see right here. So 3 single lines. So just to reinforce what we've learned so far, how many bonds exist within an H2 molecule? We have it right here. And as you can see, it's just 1 single bond. Single covalent bond, obviously. How many lone pairs exist in a chlorine molecule? So lone pairs, and it's talking about the entire molecule. We're not specifically asking about one singular atom. So we're going to count all the lone pairs. So this right here is a bonding pair, so BP. All of these that I'm squaring off are lone pairs. So we have a total of 6 lone pairs in this molecule. Now we learned so far about single, double, and triple covalent bonds, but we can actually further describe them. and we describe them in terms of how their electrons are being shared. So they can either be shared equally to form a pure covalent bond, or they can be shared, but one of the atoms is gonna hog, that's how I like to think of it, it's gonna hog the electrons more than the other atom. In this case, you will end up having a polar covalent bond. So pure covalent bond, you have basically two atoms that are the same usually. The most common example is whenever you have two atoms that are the same and they have a bond between them. Now, these are the two elements that we just saw previously, but both of these have pure covalent bonds. Polar covalent bonds, you'll have one of the elements will have a higher electronegativity. So electronegativity is how much an atom will like to attract electrons towards itself. So how much it wants electrons. Now this is actually a trend that we can generalize on the periodic table, and it actually increases this way. So I'll just draw it this way. So as you go from left to right on the periodic table and down to the top, you will see an increase on electronegativity. So the further you are in this region over here, the more electronegative this atom will be. Now we actually have values that we assign for electronegativity. These are arbitrary values. You don't have to know the math behind them. Just know that the higher the number, the more electronegative this atom is. So for example, fluorine has an electronegativity value of 4. This is the highest electronegativity value an element can have. Fluorine is the most electronegative atom. And just to show you how a difference in electronegativity between two different elements will cause, electron density to be unequal, here we have kind of an electron density type diagram where we have HCl, and we are showing here how the electron density is distributed unevenly. So it's more towards that chlorine. Chlorine has a high electronegativity compared to hydrogen. So because it has a higher electronegativity, it's going to want the electrons more towards itself. It's going to hog them more. So more the electron density is going to be over there. And what you end up having is a polar covalent bond, where you end up having a difference in charges. So these are not ionic charges, they are partial charges. That's what we call them. And we denote them with a Greek symbol delta. So chlorine is partially negative, hydrogen is partially positive in this polar covalent bond. So just to reemphasize or kind of reinforce some of those trends that we've been learning about, electronegativity versus electron affinity. Electron affinity has to do with the energy released whenever a gas phase atom acquires an electron, so it gains an electron. So it's an actual value in kilojoules. Electronegativity is just, again, like I said, it's an arbitrary scale. It's made up, and it's how attracted an electron is to an atom in a bond. So the higher the electronegativity for fluorine, the more it will hog those electrons. So how does this electronegativity difference affect how we describe bonds? We basically all we've said so far is that if you have a difference, you're going to have a polar bond. But we actually have a numerical difference that we, like a scale that we already have set out. So if the difference is less than 0.4, we classify this as just a pure covalent. If it's anywhere between 0.4 and 1.8, we call this polar. If it's anything greater than 1.8, this is just completely ionic. So it goes from just unequally sharing the electron. One atom is kind of hogging the electrons more, but they're still sharing them, compared to ionic, where one just takes it away completely. So that's why the bigger the difference, then it's going to be closer to being an ionic compound. And again, like most things that we learned about so far, this is general. It has exceptions, so keep that in mind. And again, just to give you a visual, A pure nonpolar, or we also call this nonpolar, the electrons are shared equally. This is anything between 0 and 0.4 difference. Between here, we have our polar covalent bonds. You will have a slightly negative side and a slightly positive side to that bond where they're shared unequally. And then for anything greater than 1.8 to 2, you will have that ionic bond where the electron is just completely transferred from one element to the other. So let's practice looking at these different electronegativity differences for certain types of bonds. So here we have bond polarities in the structure of protein. Using these values given in this table, arrange the following covalent bonds, which are found in amino acids, in order of increasing polarity. So from least polar to most. So let's just go ahead and order those. So we have CH, CN, CO, NH, OH, and SH. So here we see that we have CH and SH, and they both have a difference of 0.4. And these are actually already in order. So this is just to show you how different bonds can have different polarities. So CH and SH, obviously they have the same, so they're the least polar. And then we have CN with a difference of 0.5, NH 0.9, CO 1.0, and then OH a very big difference, 1.4. So this is actually already in order from least to most. So now we've talked enough about the basics, and we are finally ready to begin learning how to draw Lewis structures. So I want to point out that this will be your foundation for drawing structures in organic chemistry. You may have heard from friends, or you may have seen memes or something about how there's a lot of drawing, specifically hexagons in organic, and that is because you're drawing chemical structures. And drawing these chemical structures is based off of Lewis theory. So if you learn this topic well, starting organic will be a lot easier whenever you finally get into that class and you start to tackle those very tough subjects in there. So we're going to learn how to write these Lewis structures using the octet rule. So first, for simple molecules, all you do is you pair up unpaired electrons. So for example, we have hydrogen and bromine. We know that hydrogen likes to form a duet, and bromine is an atom that likes to have an octet. So what you're going to do is pair those unpaired electrons right here. You pair them, you form that bond, they're both happy. Hydrogen has its duet, bromine has its octet, that's it. So it's pretty simple with things like that. Now, for example, now we have 2 hydrogens and we have 1 sulfur. Each hydrogen has 1 unpaired electron, and then that sulfur has 2 unpaired electrons right here. So what's going to happen is that each of those hydrogens is going to form a pair with both of those unpaired electrons on the sulfur. So again, you just pair them up. Here we have nitrogen. Each nitrogen has 3 unpaired electrons, so they come together and then they form 3 bonds between those 3 unpaired on each, and then they form a triple bond right here. So it's 6 electrons total being shared between the 2. Now, for more complicated structures, there is a procedure you have to follow. So just have this procedure with you anytime you need to draw a Lewis structure. Eventually, you will draw so many Lewis structures that you will get tired of it. You just end up learning it. And specifically for practice problems about drawing Lewis structures, this is your go-to guide on how to do that. First, you're going to determine the valence electrons. Next, you're going to draw the Lewis structure, the skeleton structure, where your central atom is the least electronegative atom, and then you start by connecting with a single bond, the other elements. We're going to practice this, so don't worry, but then you will distribute any remaining electrons you have from that total as lone pairs to complete octets on your outer atoms. From there, you place anything else you have left on your central atom, and then you rearrange in order to make everything happy and have an octet. I'm going through this quickly because reading it is not what's going to help you learn. Actually, actually practicing it is what's going to help you learn. So I mentioned this earlier when we first started talking about Lewis symbols, but there are some common bonding patterns that I want you to keep in mind, because this will help guide you and help you determine whether your Lewis structure makes sense or not, and whether that's the best Lewis structure. So carbon likes to form 4 bonds and 0 lone pairs, nitrogen 3 bonds, 1 lone pair, oxygen 2 bonds, 2 lone pairs. You get the gist. You can use this as your guide. And this has to do, again, with valence electrons. So the reason carbon likes to form 4 bonds is because it has 4 valence electrons already on it. The reason nitrogen likes to form 3 bonds is because it has 5 electrons. So 5 plus 3, that's 8, the octet. And again, you can go through any of these and kind of see that pattern. So let's go ahead and practice. We have silicon bound to 4 hydrogens. So we're going to draw that one first, and then we have nitrogen and oxygen. So this would be nitrogen monoxide. This one has a common name called silane. I didn't want to say the actual name, but we're just looking at their Lewis structures for now. So we have SH4. First step, determine your total valence electrons. Oh, sorry. There we go. Silicon is in carbon's group, which has 4 valence electrons. So 1 silicon, 4 valence electrons. So we're doing step number 1. We're totaling the valence electrons. We have 4 hydrogens. Each hydrogen has 1 valence electron. So we have a total of 4 from, this is 4 right here, plus those 4 from silicon, that's 8 valence electrons. Okay, next. Draw your skeleton structure. Your central atom will be the least electronegative element. Another way that you can tell this is because you can tell this easily is just by looking at your formula. Whenever you have one element that's alone, that is going to be your central atom. If you have several atoms of the same kind, so for example hydrogen here, those are going to be your outer atoms. The rule is to go by the least electronegative element, but usually if you see that case where you have just one singular element and then many of the other ones around it, that's what that singular one will be the central. The one that you have multiple of will be your outer. But again, remember that trend from the periodic table, so that's what we mean by electronegativity, right? So electronegativity increases that way. So if something is over here compared to over here, this one is less electronegative, so that one will be your central. So keep that in mind. So here, silicon is our central. And then you will start by connecting your other elements with one single bond. So you can draw that one line. That's one single covalent bond. Now from there, you distribute any remaining electrons to complete octets on the outer atoms. So let's count up how many electrons we've used up. So far, we used up 2, 4, 6, and 8. So basically we used up all of them. So we're done. That was it for our Lewis structure in this case. So this was a very simple Lewis structure. We didn't actually have to go to any of the other steps. So this is a good starting point, but let's practice this next one. So now we have N and O, and this is actually another simple one. So first we're going to determine our total valence electrons. We have 1 nitrogen. Nitrogen has 5 valence electrons. And then we have oxygen. Oh, 1. Oxygen has 6 valence electrons. Now what does this plus mean? This means we're going to take away 1 electron. So remove 1 electron. So we have a total of 11 right here. And then we're going to remove 1 right here. So what we end up having is 10 valence electrons to work with. So in this case, you only have 2 atoms. There is no central atom. So this is a very weird case when you have these very simple molecules where you don't have a central atom. So you can just start by drawing a single bond between the 2. Distribute remaining electrons as lone pairs to complete the octet on the outside atoms. So far we used up 2 electrons, right? Now we have 8 valence electrons left. We are going to distribute them. 1, 2, 3, 4, 5, 6, 7, 8. Okay, cool. So let's check if things have octets around them. So this oxygen has an octet around it. It has 1, 2, 3, 4, 5, 6, 7, 8. So oxygen's happy. Is nitrogen happy? No, it only has this lone pair up here and then this bond. That's a total of 4. So it's definitely not happy. So what do you have to do? So we've done all of these steps right now. What we have to do is rearrange our electrons on our outer atoms to make more bonds with the central atom. So we are going to move 2 of these right here to be bonds instead of lone pairs on that oxygen. So for step 5, this is what we do. I am moving these to be bonds. So now, basically I move both of these to be bonds, and now we have oxygen with 8 electrons around it, so let's count them. We have 1, 2, 3, 4, 5, 6, 7, 8, and then for nitrogen again, 1, 2, 3, 4, 5, 6, 7, 8. So both of them have the octet now. We used up all our valence electrons, so both of these are happy. This is our finished Lewis structure for this.